Hi guys, today we will talk about the push-pull converter. The push-pull. So basically the push-pull is the DC-DC converter. Let me draw it synthetically. This is the transistor Q1, this is the transistor Q2, this is the ground, and this is the transformer. It is a center tapped transformer. Then we will put the diodes for the rectification, and then the inductance and the load. And this is the ground. So this is the push-pull converter. Basically this part here is practically identical to the full bridge and half bridge converter, because basically the concept here is you have a transformer. This is a transformer, and the transformer must obey the second volt balance equation, and the voltage here must swing between minus Vin and Vin, namely the average voltage must be 0. Otherwise the magnetizing inductance will start to charge. And so here you're gonna have the positive square wave rectified, meaning that here the maximum duty cycle is 0.5. So if in the primary side you have 0.45 as a square wave used for your MOSFETs, in the secondary side you're gonna have double duty cycle, so 0.9. Why is that? Because basically you have this square waveform and the other negative, and rectified altogether is basically this, minus the dead time here. This time we will perform a current control, so we will use a controller called LTC3723. So let's check this controller online and let's see how it works. So this is the controller for the push-pull. It is a PWM controller, and this is the most typical application of this. Just a brief explanation of this guy. So this is the push-pull converter. As you may see, these are the two switches which I called Q1 and Q2. This is the input voltage, and this is the UVLO, which is the under voltage lockout. Let me write under volt lockout. Then this controller provides SPRG and DPRG. These two pins here are used for the dead time control, because in synchronous converter you must have dead time control, otherwise it will be a mess for the shorts. Then you have SS. SS is soft start. The soft start is essential because whenever you turn on a DC-DC converter, you're gonna have here capacitors which generate a lot of inrush current. To reduce this, you can use the soft start. Then to the other side you have you have two interesting things. DRVA, driver A, and driver B are the two driving PWM for the two MOSFET Q1 and Q2. GS is the compensation network with the comparator pin. which close the feedback through here. And then we have also SDRA and SDRB. These two pins are used if you want to perform a synchronous rectification. You see here that you should put diodes. You should put diodes here in this way, but you can also use the synchronous rectification like this guy did with the LTC3901. If you do this, you will end up having even better performed controller, even a better performing circuit, because these guys here are less dissipative than the diodes themselves. We will use the diodes version because it is easier, but you can find this in NetSpice, I think, and put the diodes and put the synchronous rectification like this. Then what is this? This all together with the LT1421 and the guy here provide the opt isolation and the comparator with the type 3 type 2 with the this is a type 2 ramp compensation. So now let's go in the functioning diagram of this guy, which is this. So you see that the driver A and driver B provides the square wave needed for the MOSFET Q1 and Q2. This will go to Q1 and this will go to Q2. SDRA and SDRB, we will not use them in this video, and this is basically the current how the current control works. So this in red is the ramp needed for the current control. So at the end, in the phase 1, phase 2, phase 3, and phase 4. In the first two phases, there is no control. So here it is dead. Then the duty cycle starts to rise because here you have a comparator. Let me show you the diagram, and let me give you a brief explanation of this. So as you can see, all this circuitry here is used to generate the square wave with a dead time. This is all the dead time logic that you need. Then SS is the soft start with integrated the shutdown current. Yes. And CS and RLED is the slope compensator, because you need the compensation RAM. And of course this is the PWM with the oscillator to give also this. As I mentioned before, SDRA and SDRB is the active synchronous rectification, as it is stated here. Then of course all this circuitry, all this internal circuitry must be supplied. So these have 5 volts for instance, and also this has 5 volts or something of the sort. So you need to supply this with an internal reference LDO, which in this case is 1.2. Sorry, my bad, my mistake. And this has to be supplied in all the circuitry in the system. So basically that's it. Now let's open NetSpice and let's design our let's use our LTC 37231. So this is our push-pull converter. We will make the following assumption: that Vin is equal to 5 volts and 12 volts, and we want to have a voltage output of 5 volts. Then we will make a soft start in 7 milliseconds. I already made the calculation, so there is no need to worry. So this is our Vin. Let's write 10 volts. And let's connect it to VCC. Also the UVLO must be high, and so we will connect it to our VIN. So this is the pin VIN. Now of course let's always put some bypass capacitors here with an ESR of 10 milli and 100 micro. 202 must be enough. For the reference voltage, the datasys suggests a resistance of 200 kilo ohms. This is for the dead time calculation. Then we are going to set a lot of parameters for the compensation ramp and soft start. So this is the analog ground of the circuit, and we'll put it here. I will connect CT with just a capacitor to filter 700 pico, and a soft start. This capacitor will set the internal RC, so let's put to 0.1 micro. And then, if you watch the application note, you can design the compensation ramp as you need, but the suggested value will be as follows. For the S-prog, you must put a resistor of 10 kilo ohms, and for the R-lab, just put another resistor of 500 kilo ohms. So all these values here are basically for the compensation ramps and to the soft start. You can check in depth how it is done, but I think that these values are quite enough to perform a current controller without thinking so much. Now let's use the other part of the circuit, which is the driver A and the driver B. So now we need to replicate this structure here, and so let's use a MOSFET, a MOS. Let's use I don't know. Let's use someone with reasonable gate charge and with low Aron. This can be good. Okay, this can be good. Remember that in the push-pull configuration, both of these are low side, so you can put them to ground without worrying so much. But actually, you will need to read those currents here, so you won't put them to ground, but you will need to read the currents. So let's put a shunt also for the current limitation. Let's put a 50 milliohm shunt. You can directly connect it here, but I won't suggest to do that. It's better to use a RC filter. So let's use the RC filter. Let's use both currents because they are equals. And let's put an RC. Let me draw a rectangle here. And let's use an RC. Let's use the RC filter, because these currents here are very noisy, so I would suggest 10 ohm, 100 ohm, and a value of 10 nanofarad, something like that. Something like that. So a filter which works in the range higher than the switching frequency, so higher than 1 MHz. So it must be a very which works in high frequency range. And now we should connect this to our transformer, which is made like this. In the center you have the input voltage, as I put it here. Let me put a big value of this, 1 milli, 1 milli. And I could do the same to the other side like this. Or you can even put just one. Is the same. Let me put the diodes. You can either put them in like this. In this configuration it is suggested to put like this. Let's close the two diodes. And so this is just an half bridge rectification. And let me put 2 inductances of 20 micro. These are coupled. So let me write K L1, L2, L4 equal to 1. So these are coupled. And I drew it terribly. Okay, so this is our bridge. And now you should connect to the these are 2 parallel inductors. So let me connect now the load, the capacitor filter of 50 micro, and the load of, let me write 3. And this is the output voltage out. Let's put Schottky diodes because they are faster and also less dissipating. Everything is connected to ground, of course. So now you need to design the compensation network and the compensation network and the feedback. So we will take the output voltage. Never do this, okay? Never take the output voltage like this because you can destroy this pin. Basically, this pin has something called VEH and VEL, okay? And since VEH is less than 5 volts, you can't do this, okay? You have to design a divider here. Always a divider. So let's put a divider of 1/3, 1/3, so 50.8 kilohms and 5 kilohms. Now the compensation ramp, the compensation network, can be a type 2, so just a resistor and a capacitor. In this case, in this design, the suggested values are 5 kilohms and 0.006 micro. If I did everything correctly, this should be our pull-up system. So let me save this as push-pull DC-DC. Let me run. This can be quite hard to do, so I will not be surprised if it doesn't work at the first try. Okay, so don't be alarmed because this is not an easy task and not an easy simulation. So let me check first this. Okay, it is switching and it shouldn't, because I should have put a soft start. Let me check. You should be. This should be fine, actually. Maybe this, maybe the filter was too much. Ah, sorry, the compensation there was a 0. No, it is no, it is correct. No, it is correct. No, it is correct. 75 milli, 75 milli, 1 milli, 1 milli. I think that everything is correct. Let me decrease the load just a bit. But anyway, don't know why the soft start isn't starting. It should be. But um, but anyway, so here we have okay, this is my mistake. Let me use okay, now I see it. So okay, now we have the soft. Okay, sorry, my mistake. There was the command startup which I actually forgot. So let's see step by step what is happening in this circuit here. So first let me put the thing like this, and let me can I shrink the circuit a bit? I think that I can. Yeah, I can shrink the circuit a bit, and this will be very useful also to for further reading. Let's just wait a moment. Okay. Okay, so now you can see it. So let me explain something. The soft start is a technique to avoid inrush currents and other problems. It starts by doing some very small pulses like this, and then after a while it starts the correct duty cycle. So now you can see it, the real soft start in this way. If you check here, there are a lot of pulses, small pulses, and if you do check the current here, which is flowing here, you see that there is so much inrush current. There is no inrush current at all. Yes, there is a bit, but very contained. Because there are so many peaks contained in contained in a small time. And then, after a while, it starts conducting, switching, like actually should. Let me check also the current here, the voltage here. So as you can see, as we predicted, this voltage here, which is the current here, is very noisy. And if we check the current read here, is perfectly filtered. Which is something very important in current control, because otherwise you will read these horrendous peaks, which is something that of course you don't want. So this RC filter is fundamental. Now, let us check also the comparator pin. This is the comparator which starts from 5 volts and then decreases. And this is of course the feedback, which is the same as the output voltage, but if you multiply it by 3, you should obtain the output voltage. Sorry, it is not by 3, but it's something very near at 3, not 3, but I don't know, 3.5, 3.6, something of the sort, by the way. You don't need a gate resistor, because there is no ringing or some sort of the sort. And I think that we designed our push-pull with a soft start, and we have our 5 volts. Beautiful, done. We have 5 volts at the output, and the diode has not so much drop, as you may check here. So you have the voltage which is between -12 and 12. This effect here is given by the dead time. As you can see, this is given by the dead time. So here you have basically the this time here, which is 300 nanoseconds, more or less. And if we increase the load, if we increase the load to 1 ohm, and we check again the simulation, just wait for a bit that the ramp is increasing. The duty cycle will change accordingly to the control, and it will still keep to the nominal 5 volts. As you can see, we have always 5 volts with a very low ripple. Even though there is this drop voltage of the diode, you still have 5 volts. So I think that we can conclude this video here. Thank you guys for your attention, and see you in the next video.